And I am a postdoc researcher at the Princess Margaret Cancer Center. And this is a lecture about machine learning and and an introduction about it, and contains many tips and suggestions on how to use it in your research. And usually there is a main part about some theoretical tricks and suggestions and best practices that I gave this lecture, and then there is the R part about exercises. But maybe we can just, I will shorten the theory part, and so we can go straight to the code part. And so how much time do I have in total?
Just like an hour.
1 hour?
Yeah.
Ah, okay. Let's start. First of all, this lecture, I did it already the first time last year in January at the University Health Network, and then I had this idea to write this paper that's called 10 Quick Tips for Machine Learning and Computational Biology that got published 1 month ago. And I wrote it all by myself from taking inspiration from a lecture, from some general suggestions about machine learning. I really suggested to read it and to study it, because I wrote it like for the layman, for people who don't know anything, and I try to be as simple as possible in explaining all the concepts and everything. So this is my first reference that I suggest you to follow. So we will see some introduction to some main concepts of machine learning that I really would like you to understand, and then we will work on an exercise on k-nearest neighbors, that is a popular algorithm for binary classification. First of all, what is machine learning? Machine learning is, or it's called also computational intelligence, data mining, pattern recognition, is a subfield of artificial intelligence. So if you hear these other terms, don't think it's something different. It's always the same thing. There are different definitions of machine learning. I reported here a couple of them. This is from Arthur Summer in 1954. Machine learning is the field of study that gives computers the ability to learn without being explicitly programmed. You know, there are a lot of machineries or technologies or robots that you just program them and maybe you can control them. What's different in machine learning is that the computer, the machine, the robot is able to learn something among his practice. I put this image that I found online. I think it's very explicative of what machine learning is, like the robot who learns how to program itself. Another definition, a little more formal, from Tom Mitchell from the 90s, is a computer program is said to learn from experience E with respect to some task T and some performance measure P, if its performance on T as measured by P improve with experience P. And this is another very brief but very concise and complete definition of machine learning. So the computer can learn from a particular experience with respect to a task, if and then it's measured with a performance measure, if its performance on the task improves. That gives better results. So as time goes by, if your robot, your computer, your technology item, the more iteration it does, the better results it gets. It's learning something. Another definition that I find very interesting from Yasser Abu Mustafa from California Institute of Technology says, machine learning is the technology that enables computational systems to adaptively improve their performance with experience accumulated from the observed data. And he also wrote this book called Learning from Data. And this is another definition that I think is very simple but very complete. So from the data, you can understand something about the trend. The robot can understand everything, can understand the trend, can understand the pattern, can understand something. So let's try to do a super very simple exercise like of that simulates machine learning. For example, if I give you this series of number 1, 2, 4, 8, 16, 32, what is the next number? 64, of course. And it's interesting that I just gave you a list of data, a series of data, and I gave you a task, and you were all able to make a prediction on this task. The prediction is 64. I didn't give you instructions on, I don't know what we're talking about, any hint, any context, nothing. You just read the list of numbers, and from this list of numbers, you were already able to make a prediction. And so you learn something from data. And it's something that the machine learning program can do. Just by observing the data, can make a guess on what's going to happen. Okay? So since you are humans, so you're not software, you didn't do machine learning, now you did the human learning. But that's a good idea of what's going on. So some basic concepts of machine learning that you need to understand before doing any exercise. One important topic in machine learning are hyperparameters, that are parameters that can change the behavior of your algorithm. So they call higher level properties that can model the complexity and how fast your algorithm can work. And the very important thing is that they can strongly influence the results of your application. So, for example, this is the algorithm that we will use later also in the exercise, and it's called the k nearest neighbors. And the problem, so we start from this box A, and we are in the Euclidean space, and we have these 6 blue squares, points, and we have these 5 red triangles. The problem that we have to solve is that a new point enters the space. The new point is this green circle with a question mark. And the problem that we have to solve, that the algorithm has to solve, is it has to decide if it has to associate this new point, the green circle, to the red triangles or to the blue squares. Okay? We can solve this problem by taking advantage of the k nearest neighbors algorithm. That is, the algorithm that associate a point to the k nearest neighbor points. But the key point is the main focus of this algorithm is on the number of neighbors you decide to take. So the importance of the number k, that is the number of clusters that you use in this number of points that you use in this algorithm. So if you decide to set k equals to 3, like in this B box, the algorithm will select the 3 nearest points, the 3 nearest neighbors to the new point. The 3 nearest points are this red triangle, this other red triangle, and this blue square. Okay, and then it will compute the majority vote among these neighbors. So there are 2 triangles and 1 blue square. And so it will associate the new point to the red triangles. Is it clear? Questions? And this will be solving the problem with 3 points by selecting the hyperparameter k equals to 3. What happens if we choose k equals to 4? So if we select 4 points in the space, it will happen that it will choose these 2 blue squares and these 2 red triangles. And so we'll have 2 and 2. And now we'll choose the ones that have an average Euclidean distance that is smaller. So basically these 2 points are nearer to this circle, and so it will associate again the green point to the red triangles. Okay? Then for case, if we select the k equals to 5, so 5 points, we will the algorithm will select 3 blue squares and 2 red triangles. And so will it associate the green bubble to the triangles or the squares? Tell me. Squares. Squares. Okay. Because they are 3. 1, 2, 3 against 2. Okay. So yes.
So is it like, I don't know, a general rule almost that first it associates with whatever is in majority, and then the second step would be to see whatever it's closest to?
Yes, it's always the majority, but if there is an even situation like here, it's the distance, so the average distance. And in this case, the red triangles are near. Okay. So this example is to introduce the k-nearest neighbor algorithm that we will use later, but also to explain the importance of the hyperparameters. So you can see that just by changing one number, that is the k number of points, the results of this problem change. Because in one case, it's associated to the red triangles, in the other case, the blue squares, and so it changes a lot. And there are other cases like neural networks and so on. And
you go back to the neural. Sorry.
Sure.
Yeah. So K in neural networks. Can you just explain it further?
So for the neural networks, you would have 2 hyperparameters. One is the number of layers, and one is the number of units. And so you will have to optimize both. But it's more complicated. So if you're a beginner, I would suggest to avoid neural networks. Start with k-nearest neighbors or k-means. And so usually it is to find the right hyperparameters for a problem. The best practice is a grid search on independent subset. And I will explain later how to do it. One key point, one point that is very important for machine learning is the dataset arrangement that you have to perform before running your machine learning algorithm. There are a lot of machine learning algorithms out there. There are a lot of packages in Python, Torch, R that you can use, and they already work very well. But the importance of the dataset arrangement is pivotal because every dataset is unique, and you have to pre-process, arrange many things before starting. For once you already have the so if it happens that you don't have any hyperparameters, you can divide the dataset into training set and test set. Train your model on the training set, and then apply it to the test set once it's trained. And like, for example, 80% and 20%. But most of the times, you will have an hyperparameter to optimize. Like, for example, the k that I showed before, the k for the k-nearest neighbors. So in this case, that is the most popular, you will have to split your dataset into 3 different parts. Remember, training set, validation set, and test set. And these 3 sets must be independent. So, for example, they can be the 60% of your dataset as a training set, then 20% as a validation set, and 20% as a test set. And what you do is it will be to train on the training set with a specific value for your hyperparameter, then apply it to the validation set and see the results. Then choose another hyperparameter and reapply it to the training set. I think I have another example here. So explaining a little better. So suppose that you are working on the example that I showed before about the k-nearest neighbors, and you have the number k to optimize. You don't know before if it's going to be k equals 3, k equals 4, 5, 10, 100. So what do? You split your data set in training set, validation set, and test set, and you start with a grid search. So k equals 1 doesn't make any sense. So you start with k equals 2, and you train your model on the training set with k equals to 2, and then you apply it to the validation set, and you save the result somewhere, okay? Then you turn in the training set, you use another hyperparameter like k equals to 3, you train your training set, and then you apply it to the validation set, and you save the result. Then you go on k equals to 4, you train the training set on the training set, and then you apply it to the validation set, and then you save the result. And when you get a result that is that has a higher accuracy, you stop this grid search and apply your model to the test set. And at the end, you can understand you chose the best hyperparameter. Yes.
Why do you have to have a separate validation and test set?
Because most of the times you don't know the best values for your hyperparameters. Like, for example, you don't know what is the best k in k nearest neighbors. Okay, so you try several values of k's on the validation set. Once you find it, you train again the model on the training set, and then you apply it to the test set at the very end.
Why can't you just use the validation set? I guess what I'm asking is, like, why do you also need an extra test set in addition to the validation set?
You need it because otherwise it will give you very excellent results. Like, for example, if you use this to find the best hyperparameter, of course, in the end, the best hyperparameter will give you a very high result, very high score. And then if you reapply it here, of course, it would be excellent. But what happens really is that if you put that aside, like you do here, you will apply it to a part of the dataset that is completely untouched and new, and so it will be really the real proof that it works, if it works. For example, suppose you have to develop a machine learning method to predict the diagnosis of some patients, and of course you have a limited data set. How to know if it works? If it works on your data set, it might not work on the future patients' data sets that arrive. Okay, so what do? You take the last 20% of the data set, put it away in our folder, in our computer. You train your model, you do everything, and when you're super ready, you take it and you try. Okay. I hope I explained. So this is just to remember. I know I'm gonna give you many concepts, and maybe some of them are not very easy, or maybe I am not explaining them easily. But in this case, just try to remember training set, validation set, and test set. 3 subsets. And they all have to be independent. This is very important because a lot of people make a lot of mistakes. If you use some data of the test set in the training set or in the validation set, and your model is ready, once you apply it to the test set, it will give you results, scores that are excellent. And you'll say, oh, I'm very good, I'm so glad. No, you're like fooling yourself because you already show to the algorithm what you want to predict. So you already know what to predict. Anyway, let's go on. And this, regarding the set arrangement, one thing that is very important and very underrated is the data engineering, the data pre-processing of your data set. Once again, this is something that, a mistake that a lot of people do. You know, thinking that maybe you have to work a lot in your algorithm and set up many things and it will work at the end. We already have very strong algorithms in machine learning, and very strong libraries, and very excellent platforms. But on the other side, each dataset is unique. Each dataset has some features and some details that are unique that you have to explore. Okay, each of you have in your computer some datasets that are unique and only you can know them very well. So it's very important to pre-process them and to handle them before running the machine learning algorithm. For example, a very common mistake that people do is to treat the features in the same way, and this causes a lot of troubles. For example, this is the dataset, first 6 lines of the dataset you're going to use later. And as you can see, there are these 2 features of this cancer exam that are called perimeter and area, and they have their values that are between, in this case, 78 and 1,326. Okay, and then you have these, and generally these are between 0 and 5,000. And then you have these other features that have values between 0 and 1, or even here between 0 and 0.1. So extremely smaller compared to this. But if you take this data set and you input it inside your machine learning algorithm, the machine learning algorithm will think that you have the same meaning. So, for example, it will think that this feature data here, 0.079, is 1 million times smaller than this, that is 1,326. And of course, this is completely wrong, because this feature has a different meaning than this feature. And so you cannot put together, how do you say, apples and oranges. That's the same thing. So these are apples, these are oranges. If you just input them into the machine learning algorithm, it will create a mess, because it will think that these features are super important because their values are super high, and these features are very small because their values are between 0 and 0.1. And this is completely wrong. So what do you have to do in most of the cases, like in this case, is to normalize these features. It means to scale them between 0 and 1. Once you have the values that are scaled all between 0 and 1, then you can proceed to use your machine learning algorithm. Is it clear? Then, machine learning tasks. So do we have to finish at 7? Okay, so I'm gonna be super quick. Supervised learning, when you have a label that says true, false, or anything that gives you some truth. And supervised learning, when you don't have the label that tells you true, false, or anything. So you, for example, run a clustering to cluster data. Reinforcement learning, we are not interested now. Some examples, the words that you have to use. The columns are called, in your main machine learning problems, the columns are called input variables or features or attributes. What you want to predict, for example, the outcome here is called target feature or output variable. Each row is called training example. If you want to predict 2 values that are like here, outcome, that are recurrent and non-recurrent in this case, if there are 2, that's a binary classification problem. If it's a real value that you want to predict, it's a regression. Let's move on. Overfitting is that when the algorithm adapts too much to the training set, and then it performs badly in the test set. Cross-validation, you use one piece, like for example, 20% of the set for the validation and the rest for training set, and then you move these the part of the data you choose for each different iteration. And how to choose a programming language, start with how to choose an algorithm, start with the simplest one, because you will be able to keep everything under control and understand what's going on. And some examples are R, Torch Python, and I suggest to avoid the proprietary software like MATLAB, because then if you have collaborations with other people that don't have the license, that you cannot work together. So if you're a beginner, use R, and that's it. Then we'll go to the exercise. I already mentioned to you how it works. There is another example. And so I believe you already downloaded the code from the website and the data set that you have.
You don't have the data. It's you can see the link on the board there. You have the it's also under the events section on the website. Go there. There's a link to the data. Let me know if you can find it. Does anyone not have the data?
So that is an example I found on the internet, a set of 100 patients, prostate cancer patients that had an exam called DRE. And this exam has several features that describe it, like radius, texture, perimeter area, smoothness, anyway. And each patient is classified as benign or malignant. Benign if he has a benign cancer, or malignant if he or she has a malignant cancer. This is how the data looks like. The first 20 rows. This is the target feature of the diagnosis that you want to predict. And we can go through the code that I gave to you, and then you guys can work on it. There is first a read CSV command that reads the data, and you can use head to see the first lines of the dataset you downloaded, and then we apply the command this -1 to remove this column that is the ID of the patients that we don't need. And we shuffle the rows because we don't want them to the order to influence our prediction. And then with the command table, the command table helps us to see the number of patients that are benign or a malignant diagnosis. Then we use the function normalize to normalize data that is between 0 and 1, to scale them between 0 and 1. And
Are you all following the code?
and then there is the part that in which I already split the data set into training set and test set, which we train on the first 80% and test on the remaining 20%. And we first do it for the train, for the data set, but we also split these the data set for the labels. So the labels are the target features, B or M. So there are two separate commands. One is for the to split the data set into training set and test set for the data, and one is for the labels, so B and M. So this is the first column. You can see one. And we just try, in the example that I gave you, we just try to use the value K to make a prediction. So then we call, you can see in the code, we call the function K and N by setting this capital K to 10, and we make a prediction. And you can use the function cross table to see the results. One thing to evaluate the model performance, we can use the matrix correlation coefficient function that is already encoded. think that okay, now the exercise finally for you. In the code that I already gave you, I just split the dataset into training set and test set. Now I would like you to split them into training set, validation set, and test set. So 3 different parts. Okay. Then second thing that I'm going to ask you is to try different values of k, as we mentioned before, and then I ask you to choose the best model. It is the model that has the best hyperparameter k, and that's it. So start. You guys can start to code. If you have questions, you can ask me.
Nice.
Excuse me. Yes.
You have to set your directory to where that file is. Yeah, so maybe put everything in there. Yeah. But I've done, yeah, so
You should tell us to you which folder to start. So
so then I should say set WP. Yeah, so we just guess we'll already stick to lots of other stuff. Keep it more script there so that when you run it, it'll focus on the but I think it's yeah.
Yeah, I guess.
Yeah.
So one thing before I forget, the slides are already on my website, www.wkiko.it. My first name, my last name, .it is part teaching. If you have troubles right now with the paths of the data, remember that in RStudio you have to set the working directory to the directory where you have the data. That is, you should have a window low and on the right. You have to set working directory. Do you have that problem?
No, not that problem. So here's the question. When you say ET, is it the number of events or 80% of your data size? When you set the code training set size, was it 80% of the total number or number of events? Just number of events? Just in order to
no, the dataset is 100 patients.
Yeah, so you said 80
So you have to modify that, and you will be very careful about the indices. It should be something training set index start 1, training set index and 16.
okay. So now for this exercise, I'm guessing that I should choose the number myself, like let's say 60, and then the other one would be 20. That'd be
yes, but then you have to put here the index. Okay.
For what? Like you mean these two?
Yes, when you create a training set, information set that's correct, then the things.
Yes.
So it will be more something like
So,
this.
Let's talk about the So this is your training set size, and then you set bit set size, and
Yes, in that case it was like more
What you did is this star, which comes up here.
the training set was excluded in the set.
yeah,
But I was just doing. So what I suggest you to do is more to work.
Yeah.
And then
Yeah, so basically you don't change the
and then I will validation.
Yeah, but I tried
61 validation and equals 18, and then same thing.
oh, so you I got you. And these are the number of patients, like from 1 to 60. Yeah, from 8 to 60.
So that means
How would
so it took the summary of this
so
and gave you 38 nights. Yeah.
I don't know. One thing is that you have to have the data set to
And
the
then
and
we're gonna look at
that is
oh yeah,
the
so
second
like
working data.
means that you're like you want to select just the one column, so we're only selecting the diagnosis. Oh no, we're making
To run on first.
we're adding a column here is gonna be called diagnosis.
Yes. Just to select lines 1 and 5.
We add yeah. So now we should have one called diagnosis.
And so you
And now, okay, so now we start Here's the result and the percentage from counting.